So this lesson is essentially practicing using logarithmic properties. One of the things that should help us at least a little bit is remembering that if I have a log base b of some value, that essentially a logarithm itself as a statement is an exponent. All right. And also, if I have log base b of x equals y, the equivalent exponential is still base b to the y equals x. And the last thing, these are inverses. So the notation is a little different than what we've seen before because it's a little bit more advanced math. But that's one of our definitions of what a logarithm actually is. And in fact, a logarithm definition is the fact that it is an inverse exponential. So our first answer, log base 4 of 1. If I think about this, I pick a value to make it b, and then I can write it as 4 to the x equals 1. So this is one solving strategy if you're not sure what to do. Logarithms are a little confusing, so you can change them back to exponent form. And if I think about this, 4 raised to some power is 1. The only answer that works for is 0. So x equals 0 here. And in fact, we can state one of our properties is that log base of any base of 1 is always equal to 0. So if I have a 1 as my answer, then what that is saying is 0 was my exponent. Okay? So number 2, you're supposed to notice that what you have here is an exponential base, and then right next to a log base. And they both are a base 5. So what did we state already? These are inverses. So essentially they cancel each other out entirely, and I'm left with the only value left, the actual number that I'm operating on, which is 3. So the other thing which we should remember is an exponential base or log base is an actual operation. It is saying do something. It's not actually a numeric number. Okay. Same idea here. We have a log operation, base 7, and an exponential operation, base 7. So our bases are the same. We have a log and an exponential together, which means my answer is then -3 because they inverse each other out. Okay. Then we have this, what looks like 1n, but we're supposed to remember that's really ln. And the other thing that we're supposed to be knowing, have a knowledge of at this point, is that is actually log base e. Okay. Also, e is not variable. E is the approximate value to 0.71828 and so on, because it is a number that we have defined with a letter, because we do not want to have to write it out every time we use it. So if I think about this expanded, it's log base e of e to the 5th, and then my same rules apply. Log base e next to exponential base e reduces out, leaves me with 5. Okay, so 5 and 6 and 7. So these are just remembering our properties of inverses. The other 2, 3 are actual evaluation a little bit more. So I'm going to define this as an x value. And again, a solving strategy is convert. So base 2 log, base 2 exponential, and I switch my input output. So I can basically, my x comes in as my input, as my exponent, and my output then becomes 64. So what I'm thinking is 2 to what power is 64? So let's see. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is finally 64. So that's how I would do it without a calculator, essentially. And then I just count the 2's. 1, 2, 3, 4, 5, 6. So I multiplied 2 by itself 6 times. So my x value that I decided on has to be 6. So 2 to the 6th is 64, is what I'm basically saying. Okay. Next one, converting it in base 7 to the x equals 1 over 49. Okay. So what I know here, 7 to the first is 49, and 7 to the second is, 7 to the first is not 49. 7 to the first is actually 7. 7 to the second is 49. So I'm seeing that this 49 and this 1 over 49, there's a lot of similarities, except one is a fraction and one is not. So how do I change a whole number answer into a fraction answer? Well, that's also a exponent property, which is the fact of a negative exponent. So if I have 7, so one of the rules is exponents is that if I have a negative exponent, so if I do 7 to the negative 2, negative exponents, remember, this value negative 2 is not actually numeric. It's an operation, and it's saying do something twice, multiply 7 by itself twice. If it's negative, what does that mean? Okay, what does it mean to multiply something by itself negative times? Kind of doesn't make sense. So what we want to remember is actually what it means is opposite of multiply, which would be then divide. So we change it to a division problem, and it's saying, I'm supposed to basically divide by 7 to the second. So what I find by doing this, remembering negative exponents are fraction values, okay? So x is actually here, has to be negative 2, okay? Let's see. Now we have a little bit more of a challenge because we have this square root. So if we do log, if I don't see a base, which I don't here, the base is 10. So that's the common logarithm, square root 10. And I can kind of use my idea, okay, log base 10, base 10. Well, those are supposed to be inverses. So the only thing left is the square root symbol. Okay, so essentially, yeah, we can't write a symbol, a math symbol, as an answer. It should be a number. So, but that's basically what I'm trying to do. Okay. So probably what I want to start thinking about is, well, this is exponential. Let's figure out an exponent that works. So what I want is, I know I need 10 to some power. So I need a power there. Has to equal the square root of 10. Well, that's interesting. Let's see. Well, I'm solving kind of getting rid of the square root. So let's square both sides. So what that means then is 10 to the, I got to square this side, 10 to the 2x has to be equal to the value of 10. Okay. What's the exponent on 10? Well, that's got to be 1. And then, look, my bases are the same. I have a base of a 10 and a base of a 10. What does that mean? That means that 2x equals 1, and that means x equals 1/2. This is essentially the proof that says radical sets are fraction exponents. So a square root, so over here back on our real problem, log base 10 of 10. square roots turn into a exponent of 1/2. If it was a cube root, it would turn into an exponent of 1/3. So if that was a 3, I'd actually get 1/3. Okay? The reason why is essentially right here. So we actually did this before, but it was a little bit difficult to figure out what was going on. But basically, it's the bases are the same, so the exponents have to match. So by definition, the exponent of 1/2 has to match your square root. Okay? Back to my real problem. I had a square root, not a cube root. So that's 1/2. Log base 10, exponential base 10 are inverses. So what am I going to be left with? Just 1/2 as my final answer on that one. Okay. So that's applying your basic properties of logarithms. So my next section is being able to take an expanded set. So something with plus and minus and so on, and convert it from essentially double logarithms, multiple logarithms, to logarithms into something with one single logarithm. All right. So I'm taking this ln. Notice it's the same. And I'm going to turn that into ln. And the property that I'm using here is that if I have the same base and I have a plus sign, then I can turn it into a single logarithm with multiplication. All right. So and this is the inverse of the property. So the exponent property I'm using that I'm thinking about is a to the m, a to the n equals a to the m plus n. So logarithms is opposite, okay? So notice double base to single base as an addition. Here we have a double base as addition to single base as multiplication because it has to be an inverse set. But essentially it's the opposite of this exponential property, okay? So the property is actually log base a of m plus log base a of n equals log base a of mn. All right? Second property is minus. Well, if plus is multiply, then minus is actually divide. So that is the property. So log base a of m minus log base a of n combines into log base a of m over n. Okay? These actual exponential properties are logarithmic properties you should already have written down in your notes, but I'm just reviewing them quickly for you. Okay? So there's my first answer. Forgot to circle it. And I'm doing the same thing. I see log and log. Remember, this is base 10. If you need to write it in, go ahead and do so because you already have a base. The base is not u or v, it's base 10. Okay, common log. So what I have is log combined from 2 to 1 of u over v. So I've just used my combination property. Okay. The next property is that if I have, going from the exponent property of a to the m to the nth equals n a to the m, sorry, that's not what it equals a to the mn. Okay, so remembering that essentially exponents are logarithms, I'm pretty much saying this is an exponent, this is another exponent, so it's like an exponent multiplied, so I can switch it from here up to here as an exponent. So what happens is this 1/4 can change from a regular multiplied number, so log base 6 of x, and that x can turn into an exponent base to the 1/4. All right. And just FYI, if I wanted to continue, I could write that as log base 6 of the 4th root of x if I wanted to, since fraction exponents are radicals. So the 4 to the 4th root. Okay? All right. So now what we're trying to do on the next 4 problems is essentially combine the properties we did in problems 1 through 3. All right? So one of the things is I cannot be running around combining a plus sign into multiplication with this 3 on the front, because that 3, if I change it to multiply, it's like it needs to distribute, and it's not going to distribute into both sides, okay, because it only belongs to this piece. So I need to get that 3 somewhere else. So the property I apply is moving it up. So log base 7 of x, and I can change it from a 3 in front to a 3 on x as an exponent, so it moves, okay, plus log base 7 of 4, nothing happened there. So now I have the plus sign, and I just see that I have a log, and a log. So then I can combine them into a single log base 7. And what do I have on the inside? 4x to the 3rd. If you wanted, you could even put parentheses on that. So there would be my final answer there. Okay. Same idea for number 5, almost identical, except that the number in front is 5 and the operation isn't plus, it is minus. But we start off the same way. Log 2 to the 5th power, so moving it from the front up on top, minus log of 5x, and then again noticing that our logs are the same. Remember, if you need to write that in, those are base 10. So if you don't see any base, the base is 10. Okay, both log base 10, so I can rewrite that together as log. And then inside, I essentially have 2 to the 5th over 5x. And that would be my answer. Or if I really wanted to, I could write log of 32 over 5x. But essentially, the problem set is the same. If you want to be really clear, you can always add some parentheses. I'm just going to say that's my final answer. Okay? So then 6 and 7 are the same idea exactly. Okay, only on this one, I actually have a 4 and a 3. So I need to move both first. So ln of uv to the 4th minus ln of vw to the 3rd. And I will make a note that you need to be careful here because 4 is to both of those, okay? So this is uv to the 4th, which would equal u to the 4th, v to the 4th. It is not uv to the 4th, okay? So the 4 belongs to both of them. So you either need to do the parentheses. So either the parentheses or the 4 goes on both of them, okay? So be careful there because what I'm saying not is be careful, you don't want that. That is an error, all right? Be careful with your notation. Parentheses are your friends. So now I'm going to combine it. ln, remember ln is really log base e, okay? And then it's minus. So minus turns into essentially division. So what goes on top is uv goodness. UV to the fourth over VW all to the third. That would be my answer for that one. Okay. On 7, I don't have anything out front. I just have a plus. Plus things multiply the input set. So, and these are both just log. Remember, it is log base 10. So if I need to put the 10 in there, I can. So log base 10 is the one I have where I don't see anything. And then my inputs become x minus 4 times 6x plus 5. And I personally would say that was my final answer, because if you choose to multiply it out and you have an error, you don't do something right, then you will lose points because your answer is incorrect. Right now, that answer is correct. So this answer right now is correct. So I personally would just stop here. All right, so this section, problems 1, 2, 1 through 6, is basically practicing with, I have an expanded set. So I have an expanded set with numbers and pluses and multiple logarithms in the same problem. And I'm applying my log properties to combine it from like a double logarithm here, 2 logarithms to a single logarithm. Okay, so that's going one direction. Expanded to condensed. We should also be able to go the other direction. Condensed to expanded. So now I want to expand. Okay, so what I'm noticing is, what am I doing here? This is multiply. So multiply splits up. So my log splits up into log of 5 plus log of x. All right, next one, I'm dividing. So I'm dividing on that one. So that splits up into log of 5 minus log of x. Okay, number 3, obviously it's not multiply or divide. What it is an exponent. Okay, and if we can bring exponents from the front up to the top, what we want to do is bring this exponent down in front. So exponent to exponent can be written as multiplied exponents. So 5 goes in the front, log base 7 of x. So 4 is, let's do a couple things. First of all, I need to split up my problem. So the first thing I'm doing is noticing that essentially it's x squared times e to the x. So let's split it up. So I have ln of x squared plus ln of e to the x. Looking at now, I'm going to look at the first set. So what I see is there's an exponent of 2. So let's bring that 2 down in front. So 2 ln of x plus. Now let's look at the second set. And what I notice is I have ln, and what I'm remembering is that's log base e, and I also have e. So what does that mean? Well, let's remember that means that they are inverses, logarithm, exponent, same base. So they cancel out. So what am I actually adding? Just x for this one. Because ln and e next to each other will reduce out since they are inverses. All right, so the next one, there's a couple different ways to do this one. I'm going to start off with the fact it's a division problem because that looks easiest for me to tackle first. So that's going to be log base 6 of the 4th root of y minus log base 6 of the 4th root of x. And then I'm remembering that I can do something with these fourth roots. And what I can do is change them into an exponent. So basically a radical index of 4 becomes a fraction exponent. So I can change that into log base 6 of y to the 1/4 minus log base 6 of y. Oh, sorry, that's not y. That's x to the 1/4. And now I've changed it into an exponent. So now it's an exponent, which means I can rewrite it in the front. So my final answer, 1/4 log base 6 of y. So moving it from being an exponent out to being a multiplier, minus 1/4 log base 6 of x. I'm doing the same thing on the second set. And then that would be my fully expanded answer. So the idea on expanding is I shouldn't have any exponents inside the logarithms, and I should also not have any operations. So no multiply, actually specifically no multiply or divide. If I had log base 6 of x plus y, you cannot split it up like we did. I'm done, okay? Because what actually splits is multiply to addition, division to subtraction. And notice it's splitting from 1 to 2. So if it's already added, you're just adding your input and you're done. Last thing we need to talk about is what's called changing the base. If I have a value like log base 7 of 49, okay, this is kind of what we did at the beginning, I should be able to figure out that that's 7 to some power equals 49, looking at it as an exponent, and then knowing that 7 squared is 49, so then my answer is 2. All right, and that's great if I have just regular power values, regular exponent values like 2, 3, and 4. The problem is, what if it's not 49? What if it's something like, I don't know, 33? Well, now I've got a question mark. 7 to the 1 is 7. 7 to the second is 49. 7 to, I really don't know, is 33, right? So I know it's between 1 and 2, but that's all I know, okay? I know it's a value, but I can't find it easily. And also, unfortunately, on most calculators, this is because logarithms are way more complicated to do because they are inverse exponentials. On most calculators, you have a button that is log, and you have another button that's ln. So this is what you see on your calculator. So this one is log base 10. Okay, that's not anything you want. It's log base 10. And this one is log base e. And quite clearly, neither e nor 10 are equal to 7. And that's why we do this. Why do we do this? For calculation. If I need an actual number, an actual numeric value that I can actually determine what it is besides, oh, it's somewhere between 1 and 2. If I need more accuracy, then I'm going to need to be able to put it on a calculator and get a decimal value. Okay? So changing the base basically says that you switch out your input set, log base b of x, and you turn it into a division. Okay? And you choose a different base. So the base I'm going to choose, I like using ln. All right? I don't care which one you choose. All right? They work exactly the same way. And the idea is that the formatting should basically, the easy way to remember is formatting should match. So base should go on the bottom. So on the bottom goes the B. Okay? On the top goes the X. So either ln of X or ln of B, or log of X over log of B. The only difference here is in the first thing, it's base E, and in the second one, it is base X. Sorry, base 10. Okay? So that's what change the base does, is essentially I switch from this format, log base B of X, to one of these other formats, either the ln divided by ln or log divided by log. And the reason why is because I want an actual value. Okay? So now we have a couple of examples. The first one wants to use common logarithms. It doesn't actually matter. Pick the one you like because they are equivalent. But if we use common logs like it says, what it's going to be is log base 9 over log base 6. And then I can input it into my calculator. You should do this and verify that you can actually accurately get the same answer that is going to be on the screen. So my calculated value, 1.226, strongly 3 decimal places is what I'm looking for. Okay. I will note that if you chose to do ln of 9 over ln of 6, it is going to be the exact same answer. All right, so next one, I want to see, this is your work on your paper, by the way, because I need to know if you understood what you were setting up. So can you set it up? That's step 1. Can you input it in your calculator? That's step 2. So bottom number goes to the bottom, base to the base, and top to top. Choose a log value, choosing log. Okay, answer, once you calculate it, log of 3.5 divided by log of 6, 0.699. Okay, so there's your 2 examples using logs, common log, and then they want you to do 2 examples using ln. So ln of 8 over ln of 3. Again, if you want to check it, you can also put in log of 8 over log of 3 because they are identical answer sets. Okay? So let's see. ln of 8 divided by ln of 3. And this answer is 1.893 rounded off to 3 decimal places. And then the second one, ln of 4.12 divided by ln of 2. So on your calculator, ln of 4.12 divided by ln of 2. And 2.043 rounded off to 3 decimal places. So the purpose of changing the base formula is so that you can actually get a numeric value versus a math number value. They're all numeric, but essentially some are, if we want to actually have a value that we can understand, then we need to convert it to a decimal point value, essentially. And that is the end of the notes for logarithmic properties.